Hi everyone, in this video we're going to look at predicting the products of an acid-base reaction. So when you have two compounds on the reactant side, how do we know what products are going to be made and which of those is going to function as the acid or the base? So let's start with something pretty straightforward. Let's say we have HCl and ammonia, NH3. I'm going to throw in this equilibrium arrow right now. In another video, we'll talk about the types of arrows that we put here and how to decide which ones to use. So for now, we're looking at this and we say, okay, well, what's going to happen here? All right. Well, if we are talking acids and bases, more than likely this is going to be an acid-base type reaction. So we need to identify which species is the acid and which species is the base. Okay, so keeping in mind our definitions, acids have protons. Okay. Both of these have protons. Then bases have electron pairs, right? So these both have electron pairs. While the chlorine here does have pairs of electrons, comparing a neutral chlorine atom to a neutral nitrogen atom using our atom rule, so this is a great time to apply those ARIO rules as well as our pKa values. If we do that and compare these two atoms, we find that they're not in the same row or same group, so atom size is going to be the predominant factor here. Chlorine is a much larger atom than nitrogen, and so it will not be as basic compared to nitrogen. And since the name is hydrochloric acid, it is rather obvious that this will function as the acid and this as the base. Okay, so we can use some of our rules, some of our intuition, and maybe a little bit of nomenclature to get these predictions right on. Okay, so then we can use our mechanistic theory and say, okay, well, what is going to happen here? All right, well, the electrons are going to reach out and grab the proton. And at the same time, that proton chlorine bond is going to break. So that gives me Cl minus plus NH4. And if we account for formal charge, it would have a +1 charge. So then we can label these as the conjugate base. Right? It has lost a proton, and then the conjugate acid, it has gained. And if you have trouble, remembering that, then just look at these. Which can function as a base, which can function as acid? Chlorine doesn't have any protons. Chloride doesn't have any protons anymore. So it has to be the base. And then nitrogen with 4 hydrogens doesn't have any lone pairs. So it has to be the acid. So they are the conjugate base and the conjugate acid here. Now let's look at another example. Let's take the compound phenol and react it with, let's say, ethoxide, CH2O minus. So ethoxide is related to ethanol. It has lost a proton here. And typically this comes as a metal salt, right? You can't buy a bottle of a free anion. It's got to be paired up with some counter ion. So now let's look at these and say, well, what's the acid and what's the base here? All right, phenol. We, look at this and we say, okay, well, this oxygen has a proton. pKa of OH bonds is typically around 16, but it has this benzene ring on here, and so phenol is a special case where the resonance stabilization brings that pKa down to around 10. All right, then if we look at ethoxide, all right, so it does have a negative charge here, and these hydrogens here would have pKa's around 60 since they're regular alkyl hydrogens. So the lower the pKa, the stronger the acid, meaning that phenol would be the most likely to function as the acid here. So I'm going to go ahead and write acid, and then we just want to confirm that the base does have protons, and it does here, and a clue right up front would be, okay, we have negative charge, it's electron rich, it's going to function as the base. Okay, so again, using our curved arrow notation, we have the electrons from the base grabbing a hold of the proton, and then the proton oxygen bond in this case is going to break. So we end up with O minus, since we have gained that pair of electrons, and then we have the conjugate acid of ethoxide which would be the neutral ethanol, and then label these conjugate base, conjugate acid. All right, now let's try one last one. Let's try a couple more. So here's one that may be a little bit more difficult for you. We have cyclohexene, so this is an alkene, carbon-carbon double bond, remember from your brief OChem review in Chem 110. And then we have HBr, which is hydrobromic acid. And so if we look at these and we say, okay, well, HBr has protons to donate, the alkene has protons to donate, there's alkyl protons and also alkene protons out here. So assigning pKa's, the pKa of these alkene protons, the so-called vinyl protons, are going to be about 40 or so. These protons, alkyl, are going to be about 60. And then here with HBr, we have pKa's around -9. So obviously, this will be the acid, and then this would have to function as the base. Okay? The bases have electrons, so while there are no electron pairs here, I did say that double bonds could function as bases, right? They have those pi electrons are easily given up. So we use our curved arrows, take this pi bond to our acidic proton, break the bond, and we end up with a hydrogen being added. So we started with one, so I'm just going to draw them all in here. And since we took electrons away from this site over here, we're going to have a positive charge. And since this alkene is symmetrical, both of these sides are identical, it doesn't really matter which one of these has the positive charge. When they're not identical, we'll talk about how that goes later on in the course. But this would be our product pair. We have the conjugate acid here, which has gained the proton, and then the conjugate base, which lost the proton through this process. And there's one more type of consideration that we might have to make here. Let's take acetic acid. If we react this with HCl, we're going to have to make a decision here about what's going to function as the base, right? Acetic acid, hydrochloric acid, they both are well-known acids. So where do we have electrons? We have pairs on the oxygens and pairs on the chlorine. If we use our atom rule again, chlorine a larger atom, less basic. So oxygen is going to be the best base here to pick up any protons. So then we have two options, right? The carbonyl oxygen can reach out and deprotonate the HCl, or the oxygen from the OH can do the process. So what do we get? Let me draw these both out. So if we go by the green arrows, we would get this conjugate acid. And if we go by the pink arrows, we would get this conjugate acid. All right, so then we need to think about, well, what can I look at in order to determine which of these is the best conjugate acid to draw here? So let's think about our rules. Atom rule. Oxygen, it's the same atom in both cases. Then we go on to resonance. So resonance is going to tell me that if a conjugate base, right, so in this case, if these are our acids, then this can be thought of as the base, which it's acting as one in this reaction. Bases are more stable when the pair is delocalized by resonance. And that delocalization means that it's less available to grab a proton, right? So let's look at the carbonyl oxygen. Can we delocalize these electrons via resonance at all? Can we move them down here? Well, no, because this carbon has 4 bonds. We can't break single bonds in resonance, so there's no way to move these and still maintain 4 bonds. Okay, so there's no resonance with the carbonyl oxygen electrons. Now let's look at the OH electrons. Can we delocalize these via resonance anywhere? Well, it turns out, yes, we can delocalize these pairs, one pair, through the carbonyl to give me a resonance structure that looks like this. So the fact that this lone pair is delocalized into the pi system to give this resonance contributor means that it's not as available to become protonated. So this atom is less basic than the carbonyl oxygen. So that leads me to choose this guy as the best conjugate acid for this reaction. Another thing we can look at is that when we have the hydrogen up here on the carbonyl oxygen, this lone pair, one of these lone pairs, can still delocalize into the carbonyl, creating a stabilizing effect. So we end up sharing that positive charge across those two oxygen atoms. So both of these in the two contributors share that positive charge. And since the charge is shared, they each experience only half a charge, which is better than one atom experiencing a full positive charge. So for two reasons, we can kind of predict why this conjugate acid is favored, right? The carbonyl is more basic because there is no resonance, and then the conjugate acid here is stabilized by resonance. So there's kind of two favorable related things here. And then, of course, the conjugate base is going to be Cl minus. So we end up with Cl minus as well. And there's no fun things to discuss about that. So be aware when there are multiple protonation sites in a molecule, you have to use your rules and kind of think through which of those atoms is going to be the most basic. And important to understand why. Because if you can't explain why, then it's not useful to you down the line when you see a new and novel example. Thanks for watching this video. As you're practicing, if you have questions, please reach out.